organizers for making it possible for me to spend at least a week here with you. In trying to sort out what I would say in this lecture, I was faced with a challenge because everything you've heard for the last couple of days is about the atmosphere, atmospheric convection, in fact, moist convection, and so on. So, since my talk is really about the oceans and about turbulence in the oceans, I decided to try to make a transition that would be relatively easy for you to follow. And so I thought I'd start off by making the point that everything that I will say has really to do with testing let's call it the veracity of modern climate models. These structures are heavily tuned in order to enable them to fit modern observations. And you know, one of the main problems we face is that when we do this tuning over the instrumental era and then make projections of global warming based on an assumption of a scenario for trace gas increases, what we discover is that the family of models that have been integrated internationally display a very wide range of sensitivity. So this is sort of at the heart of one of the main issues actually that's being investigated in the global change community. So it's interesting to take a step back from the CO2 world and ask whether these modern climate models have any skill way outside of the range of boundary conditions in which they're tuned. So my talk will be about that problem and about designing a very severe test of the coupled atmosphere, ocean, sea ice behavior which is embodied in modern coupled climate models. So just to start, I thought I would show this animation produced basically of the moisture field, vertically integrated moisture field in a modern climate model. And here I'm using the CESM1 coupled structure that's been built in NCAR. And what I'm showing is an animation of the vertically integrated moisture content in the atmosphere, as well as the rain which is occurring in the system. And many of you will not know, and the rain regions are shown by closed contours. So many of you may not know that there have been huge progress actually made in the quality of climate model predictions in terms of the rain field when averaged over multiple seasons, if you like, from a given run. So everything I'm going to be talking about here is going to take this CESM1 model and challenge it in a way that will be testing not only the atmospheric evolution on very, very long time scales. I'm talking about time scales of thousands and thousands of years, with time steps in the model being on the order of minutes, right? So we're going to have to integrate this model over huge time scales, right? And we're going to be interested in the coupled atmosphere, land surface processes, and ocean dynamics and sea ice cover on these two grids which talk to one another through a flux coupler, which is not, as we call it, flux corrected. So what I'm going to do is to look back into the past at a time between 60,000 and 30,000 years ago, where a special phenomenon is known to have occurred which has never been explained previously. Many of us have tried. There are hundreds of papers of people who have tried to explain the data that I'll show you using Earth system models of intermediate complexity, which are really bad models, but we do the best we can with bad models and have done over the last 15, 20 years to try to explain the observations, which I'll show you now. So this is the primary data set, which is kind of, if you like, poster child for rapid climate change. Okay? So I'm not just interested in climate change on very long timescales. I'm interested in very rapid climate change. And the data which show that this has occurred repetitively in the past are data that are taken from the deep ice cores that have been drilled at Summit, Greenland, Um, there are now several of these cores. There's the grip core, the initial European core. There's the North Grip core that was drilled after the first European core, also by Europeans. And then there is the GISP core that was drilled by the Americans somewhat to the north. But when you look at these data, let me just walk you through them all if I can. So isotopic variability downhole in the Greenland, in the North Grip Greenland ice core is shown basically in green. Orbital insolation at roughly 60 degrees north latitude is shown in blue. Ice volume over the last 100,000, 120,000 years of Earth history is shown in red with error bars. Okay? You can see that to first order, the long timescale variability in the ice core, represented by oxygen isotopes, is tracking insolation. But what you'll notice in this period, which we call marine oxygen isotope stage 3, is that there are these extremely rapid events which are blown up on the bottom for both the grip core and the North Grip core, the two European cores. And what you'll see in this structure in terms of oxygen isotopes, firstly, is that the two cores basically reproduce one another, right? So what you're looking at is not noise, it's signal. And it's important to understand that this oxygen isotope measurement, when made in an ice core, is direct proxy for the temperature of the air from which the precipitation fell to build up the ice sheet. Okay? And this is an extremely tight connection between air temperature, right, and oxygen isotopes in the ice. Okay? And the reason for this is that when precipitation occurs over the ice sheet out of the atmosphere, basically there is an isotopic fractionation process that occurs. Just as there is a fractionation process that occurs when water vapor is lifted out of the oceans, transported towards this ice sheet, following which it precipitates. Okay? When you scale these oxygen isotope variations to temperature directly, yes? You can. The temperature of the air. Yes. Extended through the assumption, right, of a lapse rate down to the surface of the ice itself. So this is surface air temperature at grip. Okay? And when it's calibrated, the peak-to-peak variations of surface air temperature at grip are 10 degrees centigrade. Order 10 degrees centigrade, 10 to 15 degrees centigrade. But most importantly is the fact that if you look at the time scale here, which is calendar years, each of these pulses have a period on the order of a millennium, but it looks in these two samples of what's called the Bond cycle in the literature on the observational records, is that there's a ring down process which, following a Heinrich event, Heinrich events are labeled H, both in the top frame and in the bottom, right? Following a Heinrich event, there is a series of Dansgaard-Oskar oscillations of millennial time scale, which apparently decrease in time scale as time advances, and the peak-to-peak amplitude variations of which decay slightly. Okay? So on this time scale, you understand that this 10 to 15 degrees centigrade variation is basically a temperature variation of the entire North Atlantic sector of the climate system. Right? So this is an extremely important observation which can be used now to test modern climate models. Okay? And as I've said before, the test is very extreme because we're going to have to integrate one of these modern climate models at high resolution, both in the atmosphere and in the ocean, for timescales on the order of thousands of years. But most important for this talk is the fact that the pulse shape of these individual pulses is such that it begins with a very fast timescale excursion from basically cold conditions to warm interstadial conditions, as they're called, and then a slow relaxation back to the cold state, followed by another fast transition from the cold state to the warm, and the cycle continues. So these are Dansgaard-Oeschger oscillations. You can understand them physically, as a physicist, as a relaxation oscillation. It's a 2-time scale nonlinear oscillation in the system. And the issue is, can a modern coupled atmosphere ocean sea ice climate model actually capture this behavior? And this has never been demonstrated until about 2 years, when we began actually getting these results, which I'll go on to describe. Yeah, of course. Dansgaard-Oeschger, yes. Yes. What are they? Yeah, these Heinrich events have actually been understood from an oceanographic perspective for the last 10 or 15 years. Heinrich was a German graduate student who actually, looking at deep sea sedimentary cores, discovered episodically in the cores at a spacing of order 10,000 years, new events in the core that were represented by very deep layers of ice-rafted debris. Okay? And what this phenomenon, the Heinrich phenomenon, consists of is basically a massive instability off the eastern flank of the Laurentide ice sheet, which covered Canada at last glacial maximum, right? Basically, what happened in each of these events was that the ice stream which filled Hudson Strait at glacial maximum conditions goes unstable. It disgorges a massive array of icebergs out into the North Atlantic Ocean. Each of these icebergs have frozen into the base debris that has been scoured from the land on which the ice sat prior to the instability. So as the icebergs move over the ocean, the ice-rafted debris, which is basically frozen into the base of each of the icebergs, melts out of the iceberg, rains onto the ocean floor, and makes a Heinrich event. Okay? So that's physically what's going on when each of these H events occur. And the explanation that we've produced of this entire process, basically, as I'll go on to argue, describes the Dansgaard-Oeschger oscillations as the response of a kicked salt oscillator in the Atlantic, to use the language of dynamical systems, basically, right? So the Heinrich event is a kick to the ocean. The bell, the ocean, thereafter rings by making Dansgaard-Oeschger oscillations. Okay? So I want to convince you as to how we've managed to come to this conclusion. Yeah, no problem. No, I mean, the interest in that particular time window is not spectacularly important, except that it captures 2 of these so-called bond cycles in which, following a Heinrich event, there is a multiplicity of Dansgaard-Oeschger oscillations. If you look at the full record, sometimes following a Heinrich event, there are only 2 Dansgaard-Oeschger oscillations, sometimes only 1. Okay? So this particular time window is a time window in which this process appeared to be especially regular, right? And that's really why we've chosen to focus on it to start with. Okay, so this is basically the outline that I'm going to follow. So that's basically the attempt at an introduction. We're going to be going after Dansgaard-Oeschger behavior with a modern coupled climate model running at very high resolution, call it CMIP5 resolution at 1 degree by 1 degree in both the atmosphere and the oceans. The explanation of this phenomenon is going to have everything to do with the meridional overturning circulation, right? And the time dependence of the meridional overturning circulation, which occurs when the ocean is hit by a Heinrich event. Okay? Right? And so this is basically the line of argument I'm going to pursue. But this meridional overturning circulation of the ocean only exists, at least in terms of the Antarctic bottom water cell, right? Because of fine scale, stably stratified ocean turbulence, which allows the deep water that forms at the poles to be lifted back up in the vertical so that it can move back into the Southern Ocean and close the two-cell form of the meridional overturning circulation in the Atlantic, which is shown here in this cartoon from John Marshall and friends. So I'm going to use this cartoon basically as a takeoff point first, just to discuss a little bit of the physics of the meridional overturning circulation, because the different varieties or flavors, if you like, of turbulence, which turn out to be involved in the Dansgaard-Oeschger process, right, are deeply connected with the time-dependent behavior of the Mach that's required to explain basically the DO process. So this basically diagram superimposes basically the oxygen content basically of the ocean as shown on a transect from the north to the south, Antarctica on the left, Greenland, Iceland, Sill on the right. So this is a two-cell structure that we're going to look at the time dependence of, which consists of a shallower North Atlantic deepwater cell, which forms under modern conditions in the Greenland, Iceland, Norwegian seas, right? Water sinks into the abyss over the sill, right? And to the south, upwelling again in the Southern Ocean. Underlying this North Atlantic deepwater cell, there's an Antarctic bottom water cell in which deep water is forming along the coast of Antarctica, sinking into the abyss, flowing to the north. And it's the upwelling of the heaviest water in the ocean up into mid-levels, which is required to close the two-cell structure of the overturning circulation. And this is mediated basically by fine-scale ocean turbulence. And so I first want to talk a little bit about the sensitivity of the results we're going to find to the nature of the stably stratified turbulence that fill the volume of the ocean and which is required to lift this deep water back up to the surface. So what I'm going to talk to you about just very briefly, I could spend a long, long time just talking about this aspect of the picture, but I'm not going to do that. I'm going to give you a brief overview of where we stand in terms of understanding the origins of the fine-scale turbulence, which is required to lift this deep water back up to the surface. Okay? And I'm going to talk to you about a Kelvin-Helmholtz ansatz for the description of this stratified turbulence. You've heard about Kelvin-Helmholtz waves and so on in the lecture this morning, and so this will take off on the pictures you've already seen of those structures. The way in which this turbulence in the abyssal ocean has been described basically in legacy models, let's call them, has been to say that there is a diapicnal diffusivity in the ocean that depends on depth, right? And in the legacy models that have been developed to describe the overturning circulation, for example, the first of which was the Bryan-Lewis model. It was used very heavily at GFDL. More recently, in the CCSM3 version of the NCAR model, the POP1 version of the NCAR ocean model, the result of which is shown in blue, based on Bill Large KPP parameterization. Okay? We basically describe the effective diapicnal diffusivity, which is required or can be used to explain the vertical lifting of heavy water in the vertical, as basically a tan hyperbolic function. In the latest version of these simple models, we have a strong tan hyperbolic increase across the main thermocline at a depth of around 1,000 meters. Okay? Recent versions of the model are much more complicated because in the deep ocean, we recognize, in fact, that there is a strongly increasing nature of the effective diapicnal diffusivity as you get closer and closer to the ocean floor. And the idea is that's associated with the dissipation of the so-called internal tide that's produced by the flow of the barotropic tide across ocean bottom mountains, if you like. Okay? So in the most recent version of the NCAR model, based on work of Jane and others, there's a hardwired structure in the model which links diapicnal diffusivity, which is shown here on the bottom itself directly to the topographic elements on the bottom of the ocean. And there's a huge problem you should understand right away, as I'll illustrate shortly, with actually employing this form of the dissipation structure in the ocean to explain climate dynamical processes that occurred so deep in the past and at a time when ocean bathymetry was massively different from modern, right? And so the tidal regime was dramatically different from modern. So there would be a real issue with employing the most recent version of the CESM1 structure directly employing this version of the tidal mixing parameterization. So mixing is an issue in the representation of the overturning circulation in these models. But just to show you an example, or a series of examples, how well previous versions of the NCAR structure have done in order to explain the double cell structure of the overturning circulation in the Atlantic. And these are earlier results of my own, which have not been published, but basically they describe what happens to the overturning circulation either in the Arctic or the Atlantic when you add one spheredrop in this frame of freshwater forcing, right, either over the Arctic Ocean, typically in the Canada Basin, or over the Atlantic Ocean between 50 and 65 or 70 degrees north. And what happens if you, in these previous low resolution versions of the model, if you force them with increasingly strong freshwater forcing applied over the region where deep water wants to form, you typically turn off the strength of the shallower deep water cell, allow the Antarctic bottom water to incur more deeply to the north. These are all steady states calculated with a version of the model at very low resolution, right? What we now want to do is to shift this structure into the time frame which is of interest to us and at very high resolution. The point which we're going to reach momentarily is that when you do that, you don't find steady states to be characteristic of cold glacial conditions, right? 0.1 sphere drop is applied over a small regime outboard of the Mackenzie River outlet in the Arctic, right? Over a period of time, 100 years typically, it's maintained for 100 years and then turned off, right? So it's an impulsive forcing. But when we look in the center of the period of time during which the forcing is applied, we find a quasi-steady state, and these are the quasi-steady states that are shown. And what's also shown here, I should say, is that we're also varying the surface conditions, right, that existed at the time in the past, either present day or during the so-called Younger Dryas transition or at the last glacial maximum itself, right? And as I'll show you in terms of examples of these surface boundary conditions, which are crucial to finding the Dansgaard-Oshkosh oscillation, right? These boundary conditions actually have a strong imprint as well on the nature of the steady states that you discover under freshwater forcing conditions. Okay, so now I want to talk yes. As rain on the surface of the ocean over an area, right? Right, as an increase in rain rate. The plots were sections, latitude and height sections, just as in the cartoon I showed you from John Marshall's work, right? Right? Which display directly the two-cell structure of the overturning circulation in the Atlantic and how it would be modified by freshwater forcing under these various conditions of surface boundary conditions. No. The water is always injected at the surface as an increment in rain rate, okay, over a finite area. And the reason these calculations were done, I should say, is that we've been able to show some years back, in fact, that the Younger Dryas transition actually occurred in response to an outflow of fresh water onto the Arctic Ocean, not in response to a flow of fresh water out into the North Atlantic, which was Wally Broker's idea, right? So this is now very firmly established, and in these analyses we're just testing the relative sensitivity of the region which is freshwater forced in terms of the response to that freshwater forcing, and basically demonstrated that whether this forcing is applied in the Arctic Ocean or directly in the Atlantic where deep water wants to form, the net impact on the overturning circulation is effectively the same, because when you add fresh water to the surface of the Arctic Ocean, it's basically exported with some time lag as pack ice through Fram Strait, basically adding freshwater forcing to the same region as you would do if you directly applied the freshwater forcing to the North Atlantic. Okay? So let me talk just very briefly about the work that we have been doing recently to understand the turbulent origins of the vertical mass flux that's required in the deep ocean in order to enable the Antarctic bottom water cell water to return to the surface in the Southern Ocean. So what we've discovered most recently is that an ansatz, an assumption as to the origin of the turbulence that's based on turbulence produced by breaking waves, where the particular wave which is allowed to break is that which is generated initially by Kelvin-Helmholtz instability through a massive roll-up of a density stratified fluid at any level in the interior of the ocean. This KH wave undergoes a massive transition to turbulence, produces mixing. Eventually, the turbulent state relaxes towards a new laminar state, and the transition basically can be described effectively through a diapycnal diffusivity, which moves mass, right, from deep in the ocean up in the vertical. So the issue is, can this ansatz actually deliver the famous Monk number, right, for a diapycnal diffusivity of 1 centimeter squared per second that Walter argued in the 60s to be absolutely required in order to allow the overturning circulation to close? So, yes? The interior of the ocean is stably stratified, right? So when turbulence occurs, it moves heavy water up and light water down, which amounts to a net flux of mass in the vertical direction. Okay? And basically the structure that you see as the flow tries to relaminarize, okay, is symmetric around the midpoint, basically, of the original Kelvin-Helmholtz instability. So this picture occurred on the cover of JFM, in which the paper describing it was produced. Of course, there are other sources of instability which are also turbulent, derivative of basically parallel shear instability. The other most famous mechanism is the Holmboe mechanism, which basically arises when a shear layer has an embedded density inversion, which is much, much thinner than the shear layer itself. In that case, the instability takes the form of two counter-propagating edge waves, right, which come into phase, go out of phase, come into phase, go out of phase, right? And many of us imagine that the actual source of instability in the oceans will be more Holmboe-like, basically because of the effective diffusivity of salt, okay, right? It's not been known until this most recent paper was published that Holmboe waves actually themselves make turbulence. It was imagined that they were very quiet little instabilities which would mind their manners and not become turbulent. But when this instability is integrated well into the regime of high Reynolds number, intense turbulence actually occurs. So these are the things which we imagine to be going on in the deep ocean, and we can infer diapycnal diffusivities from the turbulence, right? Results on the right-hand side are basically shown as a function of what we call buoyancy Reynolds number. Now, I've written the definition of the buoyancy Reynolds number. I didn't want to be left behind in the use of the blackboard, okay, so I bottom one? Here? Oh, very bottom. Okay. Well, that's very bright. So, so here's the buoyancy Reynolds number. In discussions of stratified turbulence, stably stratified turbulence, or turbulence in stably stratified flows, this number is basically a measurement of turbulence intensity. It's the ratio, basically, of viscous dissipation, right, to the product of molecular viscosity. This is not molecular viscosity, pardon me, this is dynamic viscosity, okay, times the square of n, the Brunt-Weissler frequency, which I was very sad not to have seen the previous lectures talk about the Brunt-Weissler frequency, because this is basically the frequency with which a small parcel of fluid would oscillate if displaced from its original equilibrium position, right, if the stratification in density was stable. If the stratification of density is unstable, n squared switches from plus to minus, and convection, thermal convection, or convection of a sort that I will go on to describe here in the ocean, actually occurs. So this number is very important for what I'm going to say. We can also show that in order to translate the turbulence into an effective diffusivity, right, we can do that by multiplying a flux coefficient, which is connected to the issue of the efficiency of irreversible turbulent mixing, times the molecular Prandtl number, times, again, the buoyancy Reynolds number, right? So if you look at this diagram basically on the right, what I'm basically doing is showing what happens to this diffusivity normalized with the molecular value on the left axis, but shown in physical values on the right axis. And you can see that as buoyancy Reynolds number goes up to about 100, 100, 200, 300, we actually hit the Monk number. Okay? So this is, excuse me, yes? It's the kinematic viscosity. It's the molecular value divided by the density. Okay? Right? So this is an extremely interesting result, and it's leading to the development of new parameterization schemes for the representation of the turbulence which exists in the stably stratified main volume of the oceans. Okay? And we've also very recently in a paper that's just, yes? Yes, but it was, the axes were a log axis, yes? Okay. Yes. So it's a strong function, a weak power law. Okay. Yeah, it's a weak power law. Yes, yeah, but so it's, if you look in great detail, it's a very, very weak power law. Okay, right? So here in the paper, which this was submitted actually in, well, there are two papers that have appeared in GRL. One has just come out, and you can get it on Web of Science if you go there. And what we're showing in this diagram is comparing the KH ansatz results on the effective efficiency of turbulent mixing, which is this flux coefficient, right? As a function again of buoyancy Reynolds number, right? But for different phases of the KH roll-up and turbulence transition, okay? Right? And these are being compared actually to oceanographic observations, typically from Bill Smythe and Jim Moom at Oregon State University. And also in this paper, you'll see comparisons with lake data, sure.
What is the Kelvin ansatz?
The ansatz is that stratified turbulence in the ocean that's required to affect this vertical flux of mass is delivered by the breaking of Kelvin-Helmholtz waves, not by the breaking necessarily of vertically propagating internal waves or internal wave modes in the ocean, right? So it's a test of the issue as to whether turbulence in the deep ocean could be described, right, as finally evolving from this KH ansatz, okay? And you can see basically that we capture between early turbulence measurements and old turbulence measurements the full range that have been captured in the oceanographic observations. So just to make the point that these results are now leading and described in these papers to new detailed parameterizations in terms of Pade approximates of the way in which stratified turbulence in the oceans should actually be described. Pardon? Yes, but the final process which is involved in that dissipation could very well be associated with the KH process. And if you look, for example, in the beautiful data that have been collected from the Brazil Basin, right, where you see the barotropic tide moving over bottom bumps, there are beautiful figures actually showing KH waves in the lee of the bump breaking, okay? So right? Yeah. We're making the hypothesis that in the entire volume of the ocean we could sensibly describe the diapicnal diffusivity in terms of this ansatz. To be explored, right? But at least in terms of its ability to deliver the right numbers in the range of parameter space in which the ocean operates, at least at present it appears to be very successful. Okay, so let me go back now to the problem I really want to understand. Yes?
What would be an alternate ansatz to pH?
We could assume, as wouldn't be unreasonable, right, that the waveguide of the ocean is filled with internal wave modes of various order, right? And in particular regions of the ocean, these internal wave modes could themselves achieve supercritical amplitude and break, right? And the issue would be, would they break using a shear generated mechanism like these, either KH or HOMBO, or would they break through some other mechanism? So you can imagine, and typically in the physical oceanography literature, it is imagined, right, that there is an internal wave contribution, a general internal wave background contribution, if you like, to mixing, which is never described in detail at all. Sure. In vertical scale would depend upon the actual shear which generated them, but typically KH waves always have a horizontal wavelength which are on the order of 7 times the thickness of the shear layer on which they grow, right? Right? So there will be a wide range of length scales, typically, in which this process would occur. The shear is certainly bottom enhanced, right? Right?
You really have local shear. I mean, you're really agnostic to the origin of the waves. It can be anything.
Yes.
You're
Yes.
just saying
This
small scales, local shears generated.
exactly. So it's an ansatz, and it's an assumption, and we work through the implications of the assumption. Okay, so let me go back now to the phenomenology which we're really interested to understand, which is the existence of this relaxation oscillation behavior of the ocean on the millennial timescale, which is generating massive variations of temperature in the atmosphere, right, over the ice sheet from which these data are being collected. So let me ask the question first, well, if we're going to take a modern coupled atmosphere ocean sea ice climate model and run it under ice age conditions, we need to know what the boundary conditions are, right? And of course, in the ice age, the boundary conditions were in fact massively different from modern. So we have to have a way of inferring these boundary conditions in a way that's as accurate as possible. Okay, so here's a picture of what the northern hemisphere looked like in terms of continental ice cover, grounded ice cover on the continents, during the range of time in which we're focused here, which is marine oxygen isotope stage 3, okay, where these packets of Dansgaard-Oshkosh oscillations actually occurred. So at that time, sea level was down by on the order of 120 meters on average, eustatic sea level, we call it, globally average sea level, right? So ocean bathymetry had changed massively in order to produce the water that was required to build these ice sheets over Canada, over northwestern Europe. And over Canada, for example, this ice was so thick that it reached over 4.5 kilometers in the region to the north slightly and west of Hudson Bay, current Hudson Bay. So there was a massive accumulation of land ice on the continents in the northern hemisphere. There was an expansion of ice cover on Antarctica, an expansion of ice cover in South American Patagonia, right? So the boundary conditions at that time were massively different from modern. And what we're going to have to do to get at the Dansgaard-Oskar process is to actually insert these boundary conditions into a modern climate model and integrate. Also taking into account not only where the ice was and therefore where the albedo was high, but also detailed variations in ocean bathymetry that were produced by the construction of these ice masses. So to do this, we can use a theory that I've developed over the last many years, okay? The guts of this theory is based on an integral equation for relative sea level history that is driven by any variation, space-time variation in continental ice thickness. This is basically a Fredholm integral equation of the second kind, which can be solved exactly by unwrapping it on a basis of spherical harmonics, which is truncated at some level. Okay? Right? So this theoretical structure can actually be used to determine very precisely how much ice was on the continents and taken in conjunction with glacial geomorphological data exactly where the ice was. So let me just show you a couple of examples. Yes? The input to the calculation is basically ice thickness as a function of time, okay? But we have to invert this problem, right? That's what we want to determine, okay? Right? We want to, so this poses an inverse problem for one of the inputs, okay? All right? So when we solve this problem, we have to invert its solution to determine one of its inputs, namely ice thickness as a function of time. Yes? Because there's water exchange between the land and the ocean. Yeah, yeah. Well, it's more subtle than this, because when you add, either take ice from the continents or add water to the ocean, the entire structure, form of the planet is deformed. All right? The local radius of the planet is forced to change as a consequence of viscoelastic relaxation processes. Okay? And that is fully, those processes are fully taken into account in this theory. Okay? It's yes, totally relevant, quantitatively, right? And just to show you how relevant, I'll make one further comment. Really, and because we're moving massive amounts of mass from land to the ocean and back again to in a typical ice age cycle, right? You can see that this will induce very important changes, right, in the moment tensor of the planet, right? Right? And so basically the Earth's rotational state has to be modified by that exchange of mass, right? And so in fact we need to modify the sea level equation in order to take account of that rotational feedback process, right? Which also acts to redistribute water among the ocean basins, right? And therefore leaves an imprint on relative sea level history as a consequence of this. So just to show you examples of the sort of data that we fit with this model, just focus on these data sets from Southeast Hudson Bay and from Angermanland Alvane in Sweden, the effective center of Northwest European ice and the effective near the center of North American ice. And you can see what's the form of these relative sea level histories, where time is actually determined by radiocarbon dating, right? These histories basically are almost perfectly exponential relaxations, right? The relaxation time in this process is determined by the effective viscosity of the deep Earth, and we can separate the dependence of these sea level curves from regions that were ice covered, right, in their dependence on ice thickness from their dependence on viscosity, right, by doing first an inverse problem to get viscosity from the relaxation times in these post-glacial rebound curves. And then we can actually weigh the ice, right, by determining how much ice we had to remove in order to produce the amplitude of emergence which is observed, right? Another inverse problem, right? So we take this onion skin apart, right, piece by piece, in order to infer how much ice was where. And what I'm showing you in the center picture is just a prediction of a typical model of the present day rate of relative sea level change that would be observed anywhere on the Earth's surface where at a boundary between land and sea you installed a tide gauge. What you would observe is a secular variation of sea level on the tide gauge. So this is where basically the boundary conditions come from. Not belaboring the mathematics of the way all of this works. And it generates, here's the most recent version of the model over North America and northwestern Europe in terms of topographic height with respect to contemporaneous sea level, because this theoretical structure, not only does it predict the vertical motion of the land relative to the sea, but it actually predicts the space-time dependence of bathymetry everywhere in the ocean basins. Okay? So this is the primary input now, together with the topographic variations in all other regions which experienced variations in land ice thickness. And let me go back to make a couple more comments before I actually show you the couple model integrations under these boundary conditions. So again, this is the picture I showed you previously of the legacy profiles, vertical profiles for diapicnal diffusivity. Here is the current map in the CESM1 POP2 component of the CESM1 model, the ocean model, okay? Which I've already commented, we have to turn off, right? And go back to one of these legacy profiles, and I'll use the Bill Large KPP profile. But I want first to demonstrate how different the barotropic tidal regime was under Ice Age conditions as compared to under modern conditions. Right? This is the reason why we have to turn off this complex structure. So here are basically fits to the modern tidal regime in terms of M2 amplitude. Here I'm using a discontinuous Galerkin model, very high resolution discontinuous Galerkin model of the tides. This is amplitude under modern conditions. Here is phase from the same model. And here on the right-hand side are the TOPEX data on both amplitude and phase. And you can see under modern conditions with this highly accurate model, we're able to fit the TOPEX tidal regime with actually very high accuracy. Now, if we change the bathymetry of the oceans according to the methodology just described, right, where we've removed enough water from the oceans to lower mean sea level by 120 meters, we dramatically shift basically the tidal regime. So here in A is basically the M2 present day tide. In B is the M2 LGM tide, right? And if you look very carefully, this is in B, pardon me, is the M2 LGM tide. There are massive changes, especially in the North Atlantic. That tidal amplitude goes way up, okay? But if you look here on the right, what you see under LGM conditions, glacial maximum conditions, is in fact in the Arctic basin, for example, where the tidal amplitude today is almost zero, right? Because under glacial conditions, all of the Barents Sea was covered by ice. All of Bering Strait was exposed land, right? The Arctic basin is almost a perfectly enclosed circular basin. And what happens then under glacial maximum conditions is that there's a massive tide, right, that's produced in the Arctic Ocean as a consequence of the form of that ocean basin. So we have to turn off the tidal regime. So now I'm going to show you at the end the results that we've obtained by simply integrating CESM1 under glacial boundary conditions. But I first want to show you, as this will become quite important, the variation in the, I don't know why this is not behaving well. This is basically showing the variation, the annual cycle in sea ice cover over the North Atlantic under glacial maximum conditions. And if you look at the LGM case, what you'll see in every winter, the southern extent of the sea ice front is as far south as the south coast of the Bay of Biscay, right, here in Europe. So there is an enormous expansion of sea ice to the south under glacial maximum conditions. And you could understand physically why this is happening. We have this massive ice sheet to the west, the Laurentide ice sheet, across which the air that flows in the westerlies impacts the North Atlantic Ocean, right, and induces intense sea ice growth, right, in the winter season. Yeah. We've actually argued that this is happening because you can see under LGM conditions that there are ice-rafted debris trails from what are known to have been sites of incursion of land ice into the ocean. So we think that on a micro scale, if you like, the same processes that occur to make Heinrich events are actually occurring on outlet glaciers that surrounded the Arctic Ocean under glacial conditions. Okay, so let me just describe the results of the discovery calculation. Okay, so this is now spin up of CESM1, right, under glacial boundary conditions, and there's something that needs to be said about the initial conditions, right? So what we decided to do, because we didn't want to prejudice the final result with an assumption of what ocean temperatures look like, etc., we didn't want to prejudice the results by imagining what the circulation in the ocean might have looked like, okay? And we didn't want to prejudice the flow of the atmosphere in any way. So what we did, we started using modern Levitas data for the internal temperature structure of the ocean, right? Assumed the ocean wasn't moving, right? Assumed the atmosphere was also at rest, and spun up the system from initial conditions. And these are basically shown in terms of the Mach amplitude, the strength of that upper cell in the overturning circulation as a function of time. Knowing that we started off with a hot ocean, you'll understand why the Mach spins up to about 50 spherodrams, okay? Well, more than double its modern strength. It's got to get rid of that enormous excess of heat in the oceans, right? So it hits a maximum and then begins, right, to slow down. It looks as though it's going to exponentially equilibrate in some way like this. It then, however, crosses a thermal threshold in the model and begins then to very rapidly decay, following which it looks as though it's again going to try to exponentially equilibrate, hits another thermal threshold, and bang, the Mach collapses, okay? This is, I've labeled this H because I see this as a pseudo Heinrich event. There are no icebergs in the model, right? This is just a hammer that hits the ocean, right, in such a way as to massively decrease the strength of the overturning circulation, subsequent to which the bell rings, okay? It rings on a time scale which is a little short, okay, right? This has to do, yeah? The system is a highly nonlinear system. It reaches a point, right, in which there's an enormous discrepancy between the temperature at which the system would like to sit and that at which it is currently occupying, right? So the system is highly nonlinear. There are threshold effects in its evolutionary history. Let me go back because that's actually quite important. So the red curve, okay, is basically the radiative imbalance at the top of the atmosphere, okay? So this is a very, very important point, that these nonlinear oscillations in the model are occurring around a radiative equilibrium, right, in which shortwave incoming radiation is precisely balanced by outgoing longwave radiation, right? So this is a perfect, right, oscillatory equilibrium, right, about a state of radiative balance, which constitutes these nonlinear oscillations. Also in the bottom is the coupled strength of the Antarctic bottom water cell, right? So this is a fully coupled upper cell, lower cell model, and it therefore raises the possibility that we can actually explain what we should see in Antarctica, right? Sorry? No, I mean the Mach maximum is high after the transition from cold to warm and much lower, right, after the transition from warm back to cold has occurred, right? So the oscillation is around a state of radiative balance. That's just basically the units that are used on the side. I could expand them or contract them, right? Yes, it is. Of course it is. Well, the phase relation, that there must be a strong phase relation is very clear, right? Okay. When the system is hot, right? When blue is high, red is high, which means that the outgoing infrared radiation to space is high. So when the system is warm, it's radiating more efficiently to space in the infrared, right? And the contrary in the other phase of the oscillation. So this is entirely expected. On this time scale, right? Yes. And reasonably expected.
The imbalance really tells you whether the oceans are taking up heat.
Whether the oceans are taking up heat or releasing it. Exactly. Exactly. Right?
And that's related with Jacob's overturning circulations here, which is what varies the heat, and that's with how the relation comes about.
Yeah, exactly. Because I have a finite amount of funds available to do the calculation. And this is a problem because it then remains a question as to whether with a single Heinrich event kick the system would continue to oscillate. And you can already see in this structure, which is basically the stretch in time scale that I get by shifting the diapicnal diffusivity from a constant pelagic value all the way down to the ocean floor back to the Bill Large KPP parameterization, right? Which fits the Monk number near the ocean floor, right? Right? But in both of these calculations, you can see that the Q of the oscillator is basically, it looks as though it's infinite. And that's clearly wrong because the data I've shown you of these packets of Dansgaard-Oshker oscillations show that as a function of time after an initial oscillation is kicked off, right, when you have a multiplicity of such oscillations, there is a variation both in the period, right, of the subsequent oscillations and their amplitude, right? So the model has a Q which is too high, right? And I can talk to you at the end about this if we want. But just to talk, I could obviously go on for much longer than I have. I have 2 more minutes, and I'll basically just describe to you the basic salt oscillator characteristics of the model, which has got me to describe this whole process as a kicked salt oscillator in the Atlantic, where the kick to the global ocean is delivered by the Heinrich event. Okay? So this is on the left. Well, let me look at the right frame first, because that's really the most important. So what I'm showing you here is a depth versus latitude, right, with the equator here. Okay? So this is basically the subtropical region of the North Atlantic, right? And what I'm showing you in this frame is a zonal average across the Atlantic and an average over a single Dansgaard-Oshker cycle, a time average, right? So that's the zonal and time mean of a single oscillation, right? And what I'm showing you in subsequent frames are the structure, and on each frame I'm showing you basically salinity, okay? And on each of the subsequent frames I'm showing you the same data under stadial, cold stadial conditions, and then under warm interstadial conditions. And what you can see is happening under stadial conditions. This is basically the sea ice edge, Okay? Mean location of the sea ice age under stadial conditions. Below the sea ice, right, there forms basically a region of extremely low salinity, which is basically produced by the melting of ice as it moves over the surface of a warm ocean, right? And in the subtropics, an increase in salinity, right? And in the interstadial warm state, you have exactly the opposite condition happening. So there's a salt oscillation occurring in the Atlantic that is occurring on this millennial timescale, right? Which captures the fast timescale onset and the slow timescale relaxation back to cold conditions. And these frames on the right basically show sea ice variations together with the North Atlantic mock, which show salt transport. Basically what happens as the system makes this really rapid excursion from cold conditions into warm is that there's a massive flux of salt from the subtropical gyre region of the Atlantic circulation into the north. There is a brine rejection process that's very, very important in this model in the Arctic Ocean, right? Basically what's happening in the system, and I can't go through the full suite of figures and so on that demonstrate this here, but under cold conditions there is a massive buildup of sea ice in the Arctic Ocean. Intense ridging occurs and it's driving sea ice thickness in the Arctic up over 30 meters, okay? And when the system actually moves back into the stadial state, this massive sea ice accumulation in the Arctic is disgorged back into the Atlantic, right? In the process of making the excursion back from the warm state into the cold state. I just want to show you one or two other things. This is actually the most, in many ways, it's the most important result because it's the proof that the model actually describes the physics that are actually occurring, okay? And what we're doing here is comparing data from the North Grip site on Greenland to data from the Epicadronic Modland site in Antarctica, which is basically due south of Greenland, okay? So we can do the same analysis using oxygen isotopes on the Epicadronic Modland core, and what we discover in that record, comparing first model northern hemisphere to model southern hemisphere, right, is that although we have a 10 to 12 degree centigrade peak-to-peak variation in temperature predicted for individual Dansgaard-Oshkosh cycles based on surface air temperature over Greenland from the model, right, fitting beautifully the inferences based on oxygen isotopes, right? In the southern hemisphere, we have a much muted but oscillatory behavior on the same time scale but phase shifted, okay? And the degree to which the signal is muted is by about a factor of 10. So if we've got a 10 degree peak-to-peak variation here predicted by the model in Greenland, we've got about 1 degree peak-to-peak in the Epicadronic Modland core. And here are the data from temperature data basically compared to the model for Greenland and same data for Antarctica. You can see the noise level in the southern hemisphere record is very, very high. It's a weak signal, right? But we've also done a prediction now of the signal that should be observed on the West Antarctic ice sheet, on the Waste Divide ice core, which we fit beautifully, and the record there is very, very much cleaner. So I'll make just one more, maybe two more pictures, okay? One more picture, okay? This is actually in many ways the most beautiful part and most severe test of the quality of the model. Remember, the model is coupling atmosphere, ocean, sea ice. No carbon dioxide is involved in this, okay? That's the clean part of the analysis, right? Can you take a coupled model and push it way outside of the range in which it's been tuned and expect to get anything reasonable? This is basically showing in detail across one of these fast transitions, right, that governs the Dansgaard-Oshkosh oscillation. Remember, a relaxation oscillation is a 2 timescale process, short timescale, long timescale, physical processes interacting to produce the oscillation. And what you see when you go across one of these rapid transitions, and in the model I should say that the transition is like within one winter, okay? Okay? Within one winter. Okay? What you see is across the transition before full warming occurs is that within the sea ice, and this is basically showing mixed layer depth in the ocean, right? So what's happening as you cross this transition is that there's a massive polynya that's blown open north of the sea ice front, okay, which is the first step into the full transition in the model. So this is extraordinarily interesting because if you look in the observational literature on DO oscillations, there have been speculations in the literature going back 10, 12 years even, right? That there must be something to do with a polynya in the transition process. So the fact that this model actually produces this is, I think, an astonishing success. Well, I'm going to go right to the very end. Otherwise, I'm going to get the hook. So just to comment. So I think we've explained finally the Dansgaard oscillation process. It's explained in terms of a nonlinear free relaxation oscillation of the global overturning circulation. In the Broker analysis of this process, for example, which was very heuristic, there was no model involved, but Wally's idea was that if there was continuous exchange of fresh water from the land ice to the ocean, right, in each phase of the oscillation, you could make the overturning circulation wiggle in the way which we believe it does wiggle during an Dansgaard-Oshker oscillation, right? But in these calculations, you need to understand there has been no exchange of land ice or water derived from land ice melting in support of the oscillation. Ice sheets have been purposefully held fixed, right? So this disproves Wally's idea, heuristic idea, that the oscillation demands the exchange of water between land ice and the oceans. So I think most important thing I think for this is that when what we've done is take a modern coupled climate model, the model that we use to make global warming projections, and we've asked, does it have any skill at all if you run it way outside the range of boundary conditions in which it's been tuned? And this is, I think, the main result of these analyses is that the model has enabled us to actually explain an observation that's never been explained before. So that's a real success, I think, of the coupled model structures that exist out there. Sure. No, there are other models which I think would be just as good. I mean, no one has actually followed us in this yet. But there's the group, I hope the group at GFDL will do this because their model is at least as good as the NCAR model. The European model, the ECHEM model would be very interesting to see exercised in the same way. So that's got to be the next step where we're able to compare various models' ability to explain the same phenomenon.
Are there any implications for the KH answer and how well it works?
I don't think any other than I've already attempted to argue. We've made the assumption that the turbulence that you generate with that ansatz, if it's properly analyzed, and I didn't go into this, but it's very, very important in inferring a diapicnal diffusivity from turbulence that's generated by any physical process, right? To ensure that the only contributions that are allowed to the diapicnal diffusivity are those which are associated with irreversible mixing processes. So a lot of the work that's been done in my group and with colleagues has been focused on this issue of mixing efficiency and how do you remove, right, the stirring effect, if I can put it like that, from the irreversible mixing effect that turbulence causes. And to get these diapicnal diffusivities accurately, you really need to compute them using a methodology which allows you to eliminate the impact of stirring, if you like, on the irreversible mixing process. So I've got to stop there and sorry to have gone. No. Yes. Yes. What you can see in the latter part of the record is that earlier than about 50,000 years ago, 45 or 50,000 years ago, there appear to be Dansgaard-Oeschger-like wiggles which have no Heinrich event. But the majority of MIS-3, which is unique in the record because it's a time when the ice sheet thickness on the continents was sensibly fixed, okay? Then in that range of time in the record, every Dansgaard-Oeschger oscillation, every Heinrich event is followed by at least one Dansgaard-Oeschger oscillation, right? So the bell only rings when it's kicked, would be the argument.